This video is brought to you by mywayteaching.com.
In this part, let us study about heat engines. Heat engine is basically a device which is by which a system is made to undergo a cyclic process that results in conversion of heat to work. Okay, it is a device which through which heat is get converted into work. See, this heat engine, it consists of a working substance. That working substance is nothing but the system. For example, you consider a mixture of fuel vapor and air in a gasoline or diesel engine or a steam in a steam engine are the working substances, isn't it? And the second point is the working substance goes through a cycle consisting of several processes. So that substance, it will not convert into work, but it passes some of the steps in between. So those steps are nothing but the cyclic processes. Okay, in some of these processes, it absorbs a total amount of heat Q1 from an external reservoir at some high temperature, say T1. Okay, whereas in some other processes of the cycle, the working substance releases, instead of absorbing, it also releases the heat Q2 to an external reservoir at some lower temperature, that is T2. Okay, the work done by the system in a cycle is transferred to the environment via some arrangement. For example, the working substance may be in a cylinder with a moving piston that transfers mechanical energy to the wheels of the vehicle via shift, isn't it? This is the schematic representation of a heat engine, and here it represents the basic features of an heat engine. The engine takes heat Q1 from a hot reservoir at temperature T1. Here you can see that. And it releases heat Q2 to a cold reservoir which is at temperature T2 and delivers work W to the surroundings. Here the cycle is repeated again and again to get useful work for some purpose. Okay, the discipline of thermodynamics has its roots in the study of these engines. So, the study of heat engine is very much important in thermodynamics. So, what is this efficiency of heat engine? See, the efficiency of heat engine is defined by, we know efficiency, it is represented with eta W by Q1. Okay. Efficiency of heat engine, where Q1 is the heat input. Okay, that is the heat absorbed by the system in one complete cycle, and W is work done on the environment in a cycle. See, in a cycle, a certain amount of heat, say Q2, may also be rejected to the environment. Then, according to the first law of thermodynamics, over one complete cycle, we can write W is equal to Q1 minus Q2. So eta becomes 1 minus Q2 by Q1, isn't it? You just consider a simple example here for a better understanding of the concept. For Q2 is equal to 0, eta is equal to 1, which means the engine will have 100% efficiency in converting heat to work. See, first law of thermodynamics that says the energy conversion law does not rule out such an engine, which means no engine can give 100% efficiency. But experience show that such an ideal engine with eta is equal to 1 is never possible. Even if we can eliminate various kinds of losses which are associated with actual heat engines, which means practically it turns out that there is a fundamental limit on the efficiency of this heat engine, which is set by the independent principle of nature, which is called as the second law of thermodynamics. Okay. The mechanism of conversion of heat into work, it varies for different heat engines. Basically, there are two ways. One is the system is heated by an external furnace, as in case of steam engine. Okay, the mechanism of converting heat into work, it basically there are two types. The first way is the system itself, it gets heated by an external furnace. As in case of steam engine, or in other case it is heated internally by an exothermic chemical reaction, as in an internal combustion engine. That is also possible, right? Exothermic chemical reaction. See, these various steps which are involved in a cycle, it varies from engine to engine. It will not be the same for most of the engines. Okay. Now let us study refrigerators and heat pumps. See, a refrigerator is a reverse of heat engine. Why it is reverse? Because here the working substance extracts heat Q2 from the cold reservoir at temperature T2, and some external work W is done on it, and heat Q1 is released to the hot reservoir at temperature T1. You can see that in this particular figure. It is the schematic representation of a refrigerator, or you can say a heat pump, which works as reverse of heat engine. Okay, that heat pump is also same as that of refrigerator. If it the term whether it is a heat pump or refrigerator, it completely depends on the purpose of the device, means for what purpose we are going to use that device. If the purpose is to cool a portion of the space, like inside of a chamber, and high temperature reservoir is surrounding, we call the device a refrigerator. If the idea is to pump heat into a portion of steam, for example, the room in a building when the outside environment is cold, then we call that device as heat pump. So basically, depending on the purpose, we change the name. Okay. See, in a refrigerator, the working substance, it goes through the following steps. What are those steps? The first step is sudden expansion of the gas from high to low pressure, which cools it and converts it into a vapor liquid mixture. This is the first step that happens in the refrigerator. So, sudden expansion of the gas from high to low pressure, which cools it and converts it into the vapor liquid mixture. That is the first step. And in the second step, that is absorption by the cold fluid of heat from the region to be cooled, converting it into vapor. So, that absorption by the cold fluid, okay, from the region to be cold. And this is the second step. And the third step is heating up of the vapor due to external work done on the system. That is the third step. And one more step is the release of heat by the vapor to the surroundings. Bringing it to the initial state and then completing the cycle. So the coefficient of performance of refrigerator, that is represented with alpha, that is Q2 by W. Okay, where Q2 is the heat extracted from the cold reservoir and W is the work done on the system, that is the refrigerator. When while efficiency by definition can never exceed 1, this coefficient of performance can be greater than 1. So the heat released to the hot reservoir, we can write, so we can write it as Q1 is equal to W plus Q2. So alpha is equal to Q2 by Q1 minus Q2. So in a heat engine, heat cannot be fully converted to work. Likewise, a refrigerator cannot work without some external work done on the system. That is, the coefficient of performance cannot be infinite. Okay.